Good morning. Can you hear me on this? Okay. All right, good morning. Hopefully everybody had a great fall break. You're all refreshed, ready to get back to S domain analysis. So I had forgot to put the assessment, so it's up there for today. Do make sure that you complete that. There's only one today, and then there'll be a quiz on the S domain circuit analysis. So this is now where we're going to combine the efforts that we've done before and look at the full circuit. And so we're going to go over examples today. But do note to make sure to complete that today. And then again, the quiz will be available all day tomorrow, 8 a.m. to midnight. So do complete the quiz tomorrow also. All right, any questions about that, I guess, upcoming?
What is the delta function?
So the delta function is called the impulse function, and it is to represent when you have like a trigger in a circuit. So say you have like all of a sudden something gets to a certain threshold level, then it would then trigger another event. So we just look at that as one impulse, and it just, let me see if I can find the, so it just is modeled and looks, find the graph of it. Wow. It's going to take it. So if it's 3, it just is at time 3 and there's an impulse. So it's just an infinite line, but it just is to represent when you have like a trigger in a circuit. Does that make sense?
I'm just curious as to what the trigger would be like. What would be an example of a trigger?
Just is is if your input gets to a certain threshold level, a switch, you can model a switch. Usually we model the switch as like after a time it's on, but you can do it as an impulse at a specific time. So you could model it, a switch is that way too. Most of the time it's just to represent like, oh, an event happened. And so you would represent it as that delta function. And then when you take the transform of that, it will just be a 1. So in this case, when you took the transform of 3 delta t, that's just going to transform into 3 in the Laplace domain. Any other questions? So that's the delta function, and one of the assessments does have that as an input. Actually, I think both of them do have that as an input. And so you're going to model that when you change it to the Laplace transform, it will change over to just the value 3. All right, any other questions? Okay. All right, so kind of a review. As far as what we want to do, we're going to transform the circuit into the S domain. You need to know the initial values in order to do that. And then you're going to use KVL, KCL, node voltage, Ohm's law, any other of the techniques to be able to set up the set of equations and solve those for whatever variable you want in the circuit. And it now can be any variable in the circuit instead of just the voltage across the capacitor or the current through the inductor. So it can be a complicated location in the circuit. Then you're going to manipulate that solution to get it into a match with the Laplace transform tables. Unless you want to do the Laplace transform, then you can, but I suggest that you move it to the Laplace transform tables. So a lot of times you have to use partial fraction expansion to be able to do that. And then once you do that, you can then match it up and change it back into the time domain. All right, so we're going to go through an example. So the first one here is this circuit. All right, so what do we want to do first? Okay, so we need to find the initial conditions, correct? So. Sorry. And of course, this is probably the one I don't have my solution up. Okay. All right, so we look at the initial conditions by looking at our input source. So before time 0, your source is going to be 0. So that's going to be where you're going to look at that initial time. So the circuit, I'm going to redraw that. And that's going to change your input to be 0. So V is going to equal 0. This is going to be a wire. We're going to look for IL, and then this is going to be an open, and then we're going to look for VC. So what are these going to be? So we have both initial conditions will be 0. So without a source, it's going to be 0. So then that's going to make this easier. So we don't have to draw in those initial conditions for the capacitor and the inductor. What's our next step? Okay, so we need to convert all the elements to the S domain. So that means that the values of each of these components is going to change. So what does the source become? Correct. So the 11 UT translates to the S domain as U of T is 1 over S, and then the value of 11. And let's see, R3 was 6. And then, so R's all stay the same. So 2 for R1, 4 for R2, and 6 for R3. And then what does the inductor become? It's just going to be SL, and L in this case is 1. So this is just going to become S. What about the capacitor? Correct. So this is LS. And C in this case is 0.5. I think is 2, right? Let's see. Yeah, 2 over S. So you can write that as 1 over 0.5 S, or you can write it 1 over 0.5 is 2. So you can write it 2 over S, either way. So now we're going to solve this circuit. I'm going to label this V1 and this V2. So you guys know I kind of like node voltage, so I'm going to use node voltage here. So I'm going to describe these 3 currents. So the one going through the 2 ohm is going to be what? So I start, when I have the arrow, I start at the positive side and I subtract off anything on the negative side. So that's going to start with V1. Is that correct? Anybody thinks that?
V2.
What's this node though? Is that 0? So it's not 0 there. So you would do 11 over S over 2. Were you doing the other node?
No, I have my resistance backwards.
Okay. So do you see now? Okay. All right. The one going down through the S is going to be what? Okay. What's this node here? It's what? It's going to be ground. So if you don't see it, make sure to put in ground. So that would be my V1 minus 0 over S. And then the one going through the capacitor. Correct, 2 over S. And that's one of my equations. And then Second, I'm gonna combine. So I'm just combining all of those together for V1. All right, my second equation is going to be this current, and this current. So the one through the 6 ohms. V2 minus what? Correct. The one through the capacitor. Correct. And the one through the 4 ohms. Correct. All right, and then I'm going to combine in this one all the V2s. Six. So I can solve this one for V1 and then plug in here. And now I have one equation with one unknown. I'm going to try to simplify this as one common denominator. So this becomes S plus 2 plus S squared all over 2S. And then I can invert that. So this becomes wait a minute. 11 plus S squared. Over 2S. So add an S to get those, and then you can flip the other side. So this becomes 2S over S squared plus S plus 2. So these are going to cancel. I'm going to leave it as an exercise to manipulate this algebraically to get to this form for s squared. All right, and then from here, we need to use partial fraction expansion. So we're going to get a over s plus b over s plus 0.77. And then it's going to be the conjugate again, another exercise to get AB and B prime. And this is going to be 4.4 for A, 7E to the minus 75.15 degrees. All right, how do we translate these back into time? All right, so 2 exercises to do. But once we're here, how do we get back to the time domain? Which one? Yep, so look up the tables. So we have a form of 1 over s, and then we have the e and a complex conjugate of the e. So looking at that, 1 over s is just going to translate to u of t. So the first one's just going to go to 1 u of t, and then the complex one looks like this form. It's up here. So I note here that V2 is at the same node as V out, which is what I was trying to find. So V out equals V2 here. You see that? Okay. So that's why I was solving for V2. So V out is going to be this V2. So V out of T equals what? From these 2 tables. Okay, so 4.4 U of T plus what's A and what's capital A in this one? So So it's gonna be 4.4, so 2 times, or sorry, no, 4.4, 7 for capital A, so 2 times 7. So it'd be 14. E, and then what is small a? Correct, so minus 0.77 T. Cosine, what's small b? 0.56 T, and then what's theta?
75. Is it negative 75?
It's gonna be a negative 75, so you take the negative and negative, so that becomes a positive 75.15 degrees. And then U of T. Volts. So note here that this is a plus for when this is a plus. And in our case, when we have a plus, we have a negative. And so that theta will be a negative 75.15 degrees. So when you put it in there, the negative and the negative cancel to a positive. So you do have to look and see what matches up with the plus, Does that make sense? Yes. Which one? Uh-huh. So when I look at the form here, I have a plus theta and a plus JB, and then on this one, I have a negative theta and a negative JB. So when I look at mine, I have, oh, whoops, I miswrote this, sorry. Should have been a minus here. So I have a plus and a minus, so these are opposite. So that just means the only way that they could be a positive would be if theta was negative 75.15 degrees. Does that make sense? No? How does this match up with this one? This one is expecting a plus theta and a plus JB. But the only way for that to happen is if I have a negative theta here. In order to get a plus value there. So that means that theta has to be a negative. So I have a negative theta, so the only way for that to be positive is to have a negative value of it. So theta has to be a negative 75.15. Yes, no? Think about that for a minute. All right, other questions? Are you guys ready to do your own? Somewhat. Okay. All right, so this one you're going to attempt on your own. So for you guys online, I'm going to break you up into breakout rooms. So if you want to take a picture. Oh, online, he asked, can I flip beta or B instead of A or theta? So could I write it? That's a good question. So B here would be a negative 0.56 T. Oops. So he asked if you could do this. Is that the same? So yes, you could do this. Those would be the same. So if you remember, cosine of negative t is the same as I don't know if that answers it, negative cosine of t. I don't think that helped. Um, anyway, yes, you can do the same way. All right. So go ahead and work on this. So here you're trying to find VC of t, given those values for R1, R2, and C. All right, can you guys hear me online? Okay, great. All right, okay, you had some questions about the algebra that I did, so I'm gonna go over my steps. Again, you can use other techniques to solve this. I had one person that mentioned doing a Thevenin of the beginning of this, which might have been a little bit better or a little bit easier with algebra. So converting that part to a voltage and a resistor, and then just doing the divider right away. I chose to leave it there and do node voltage. If I find node voltage, that means I know this voltage here, and then I can take this off. I can take a voltage divider between the capacitor and R2. So then this is my voltage divider equation, Vx times 1/2 milli times S over 1K plus 1/2 milli S. And then I like to simplify this. And so I typically will take 2 milliseconds times S, 2 milli times S. And then that simplifies this to Vx over 2 milli S times 1K plus 1. So that's usually the algebra that I do to get rid of that fraction kind of on the bottom. All right, so going backwards a little bit, I apologize, I am really tired. Delta T is going to be at 0, whatever the value of delta is. So this is just like the step function is at 0, you have the delta. And so this would be a delta 1. If it's at 15, it will go up to 15. So what this means is like usually a pulse in a system. So you have like a spike in the system. So this is usually a representation of that. Like how big does that spike go? And then when it's combined with like a U of T, this would be more of what you're going to see. It's going to spike up to the 10 and then decay down to the saturation value. And so it will be like a really tiny spike or a pulse. So if that helps you to visualize what that is. If it's delta T minus 15, then that would be the one at the 15 seconds. And then it would be again a spike to 1. And this can be like a really small pulse, but we resemble it as that little arrow vector up. I don't know if that helps visualize it a little bit better. What you're going to do when you change that over is that it's going to convert over to 10 over S plus 15, or you can write it as 10 plus 15S over S. So note that those are the same. So it could be 10 over S plus 15, or you can combine them with the same denominator to have 10 plus 15S over S. From there, I did a node voltage. So I did the current out of this branch was minus IS. Current out of this branch is Vx minus 0 over 1 R1. And then the current in this branch is Vx over R2 plus 1 over CS. So again, I combined the bottom. So I multiplied this term by again, the 2 milli S. So it turns into that term again, Vx over 2 milli S, 2 milli S, 1K plus 1. And then I have 1 over 1K plus that term is equal to, this is my I of S. And then I divided it by the Vx. And I had forgotten to pin the 10 to the minus 3, so that was a mistake there. So these were milli, so don't forget that milliseconds. Okay. And then from here, I think it's Josh. You following that one?
Yeah.
Okay. So from here, I again combine the bottom. So we'll take this part over here. So in order to get a common denominator there, I have to multiply the one with the 1K by 2 milli S 1K plus 1. And then the 1K stays on that top. And then I need to multiply this one by 1K on the second term to get the common denominator of 1K times 2 milli S 1K plus 1. Which is just combining the denominators to have the same common denominator there. And then because it's 1 over that, I can flip it. And so that is where this term comes from, is just flipping the bottom denominator. And then VC was the Vx times 2 milli S over 1K plus 1 over 2 milli S. Or this one, Vx over 2 milli S 1K plus 1. And so I plugged in the V of X here. So the 10 milli or 10 plus 15S over S times 10 to the minus 3. And then Vx is this portion here. Sorry, not that part. And then it's divided by this. And so those end up canceling the top and the bottom component. And then the 1K times 10 to the minus 3 cancel each other out to give you 1. And you're left with the 10 plus 15S over S. And then I just multiplied the bottom part out. So it was 2S plus 1 plus 2S, which became 4S plus 1. Did that help explain the steps there, the algebra steps there? So what I was trying to do each time is just whenever I had a fraction, 1 over something, I just try to combine those as a common denominator and then flip them to the top. So that's what I was doing algebraically there. All right, from here, it needed to, okay, you guys got that answered online. From here, I needed to do partial fraction expansion. So A over S plus B over 4S plus 1. Note too, though, that in order to get it, well, from there, I just did for A, forgot to write that. I evaluate it at 0. So I plug in 0 and multiplied the VC by S. And so 10 plus 15 times 0, 4 times 0 plus 1 ends up being 10. And then B is solving that, I get S is equal to minus 0.25. So I plug in the minus 0.25, that gives me minus 25. And then the form though is A over S plus A. So I need to get this S plus A. And so I have to factor out the 4. So that becomes B over 4, which gives me 10 over S plus a minus 6.25, which is minus 25 over 4 over S plus 0.25. And then I can match it to the table and convert it so that becomes 10 U of T minus 6.25 e to the minus 0.25 U of T. All right, questions about any of those steps? We're able to get the same doing the, okay. All right, so he did the conversion of the IS of T and the R1 into a Thevenin. And so that should yield the same result. Might be a little easier algebra with all those. So whichever way you want to do it. I always like no voltage, so I tend to go that route. Yes.
If you do a Thevenin voltage and then do it on the voltage.
Well, if you do a Thevenin, oh, that's not going to do it. If you do a Thevenin here, it's going to end up oops. So this becomes my simpler circuit between A and B. So my VTH is just going to be IS times 1K and RTH is 1K. So there's really no node. But you could call that VC and then do VC minus IS times 1K over 2K plus VC over 1 over 2 MS. My ground in there. You could do it that way. It will yield the same. Or you can just say VC here is going to be IS times 1K times 1 over 2 milli S over 2K plus. This might be easier algebra, so let me just keep going since I'm here. Oops. So that yields the same equation. That one is much easier. All right, questions? I think it's hard when you're in like thinking about things. Sometimes you don't see like, oh, this would be a simpler way to solve it. So again, you can solve it a little bit more complicatedly as you saw mine and still yield the same result. All right, any other questions? All right, remember to do the assessment. So it'll be a problem like this. Yes.
Is the assessment problem similar in difficulty to
Yeah. So I give you the end form, like this is what the end form looks like. So it would be an A plus B e to the minus CT, and I ask you what those values are.
Scrolling up a little bit, I want to see where. Yeah.
This, oh, you get this one. I mean, from year two to number, I get to number S. Otherwise, it's 15.
Just because of the table. Sorry, just 1 second. So on this, the U of T or delta T, it just translates over to one.
Thank you.
Uh-huh.
Question. Just very quick. You got this one, but in this case, what do you do? Like a supernode? Wait, you are summing up R2 by 1 SCS?
So this is one branch, right?
Yeah.
Even though these are dangling wires off of it, and this is my ground. So in this current flows, the same current flows through both of this. So it's going to be the voltage minus 0 over the total, which is summation of these two. So that's where R2 plus 1 over. Because the voltage, I mean, I could do Vx minus Vc over 1K, but then I have to write another equation for Vc, which adds another unknown. But I can note that this is all one branch. So Vc over the summation of them.
Yeah. Yes. Okay. Gotcha. Okay.
All right. Does that make sense?
Yeah.
All right.
Go back now.
Yeah. Yeah.
Okay.
When you were doing the 7 voltage right here on the highest case here,
Uh-huh.
I think I got something really confused. It's really basic.
Uh-huh.
Because I know right here that you're gonna have like I was thinking that you'd do is you'd have this, it would just become a voltage source. Is that wrong?
No, they do become a voltage. So where it's in red, there's my voltage source
Yeah.
and my resistor. The value of the voltage source. So A and B are the same location here as A and B here.
Yeah.
So
I'm
when,
forgetting something really basic.
no, it's, I think what it is that when you take this circuit, you just have to note like, okay, where's my A and B on this circuit? And so I took it right here and here.
Yeah.
And so you have to literally disconnect the R2 and the capacitor from it. If you do that, then it's left with just the current source and the R1.
This is
Resistor.
series.
And so those two are in parallel. And then to find the voltage between A and B there, if this is ground, is just this current goes through here, which is IS times 1K. And then this becomes an open when I look at the resistance. And so it's just a resistance of 1K.
Oh.
And I just have replaced the voltage source and the resistor between A and B.
So that's what I did wrong completely. I keep forgetting to add that extra resistance right there, that R1 on there. So I just had the R2 value.
Oh, yeah.
That's really
You-
important.
Yeah, you have to, this is your RTH
That affected it.
and VTH. Yep. So you have to do the whole,
All right, I
that makes
see.
sense.
Yeah, you gotta have that whole, you gotta
Uh-huh.
have that resistor there, or it doesn't really have.
Yep, you gotta include both the VTH and RTH, and it probably was confusing because they're the same value.
Okay. That makes sense. Thank you.
Uh-huh.
I see what my mistake is when I'm doing that now.
Where does the negative times 10 to the negative 3 come from?
Oh. Where does it come from?
Because I have this
Milliamps.
part. That's right.
Yep.
Okay, that's
So
what I was-
that milli, yeah.
Okay, so I think I had. Okay, then I did get it right. Okay. Could you upload those just so?
Uh-huh.
Thank you.
All right, see ya. All right, any questions online? Reed, did you have any questions? All right, have a good day.